For the prep, you need one 300 ml round bottom. So this is going to be the synthesis of titanium trisanilide. For the prep, you need one 300 ml round bottom, the stir bar, and the blue compound there is titanium trichloride tris THF. We're doing this on a 3.09 gram scale of the starting titanium complex. Rubber septum to seal the vessel. In addition, 2 vials here with the lithiated analyte in 2 different vials, so that we have one vial with 2 equivalents of ligand and the other vial with just 1 equivalent of ligand, because we're going to do 2 separate additions at different points in the reaction. Also, here is tetramethyl ethylene diamine, 1.55 grams, 1.6 equivalents, that needs to be present in the reaction mixture to stabilize an intermediate complex during the synthesis. So the titanium trichloride tris THF will be suspended in about 150 milliliters of diethyl ether. There will be a slight blue to green color change upon adding the ether, as the THF on the titanium is exchanged out for the ether molecules. The TMEDA is added. And this should result in the color change back from green to blue. Rinse out the vial, transfer all the TMEDA quantitatively. So it's good to get the reaction mixture stirring. We have a nice free-flowing suspension, the titanium precursor. And a nice blue color. Break up any titanium trichloride that's on the bottom of the reaction vessel before we're going to place it in the cold well. We want good efficient stirring later when we add the lithium ligand. That looks pretty good. So now we have the cold well here. It's bathed in liquid nitrogen, and we're going to cool the reaction vessel until the diethyl ether just begins to freeze.
About how long?
The freezing normally takes about 15 to 20 minutes.
Okay.
So yeah, we'll come back when it's frozen.
All right.
So cool the reaction vessel in cold well. You can see that it's just starting to freeze on the sides of the flask. So now we're going to just let it thaw and get it stirring. And once it's stirring at a pretty vigorous pace, I'm going to add 4.3 grams of the lithium analyte.
how the lithium analyte is going in?
Yeah, so just adding the lithium analyte as a solid. There won't be any immediate color change. But with time, the reaction mixture will go to a sort of a bright green, then to a yellow, and then to a brown as it warms to room temperature.
And we're rinsing the vial with...
I'm rinsing the vial to get complete transfer with a little bit of diethyl ether. And I'm going to go ahead and rinse the sides of the flask. Rinse the sides of the flask as well. Alright, so now, yeah, so sort of this aquamarine color. And it'll slowly turn to a nice sort of bright green and then to a yellow. When it starts to turn yellow, we'll have to watch it closely because it'll pretty quickly turn to brown. And once it turns brown, I'll need to add the other equivalent. So we just added 2 equivalents of the lithium analyte to the reaction vessel, and then when the reaction's brown, I'll go ahead and add the third equivalent, 2.15 grams. That'll take, on this scale, that'll take roughly a half hour to go through the complete color change. Okay, so the reaction has been stirring for just over 15 minutes, and this is the intermediate green color. It's just beginning to turn yellow now. In about 15 more minutes, it's very likely that the reaction will be sort of a yellow-brown, and at that point the third equivalent of the lithium analyte will be added. Just one note that wasn't mentioned earlier, the TMEDA that was added to the reaction mixture, in addition to being distilled from sodium, before use in this prep, I like to filter the TMEDA through a plug of alumina to remove any secondary or primary amines that may be present, just to make sure that they don't contaminate the reaction mixture. So before use, make sure to run the TMEDA through some alumina. So it's gone through a yellow stage and it's beginning to turn to a much darker brown. At this point, I'll add the third equivalent of the lithium analyte, again directly to the solid. I'll rinse out the vial with some diethyl ether, and then rinse down the sides of the reaction vessel with some diethyl ether as well. Alright, so this dark brown solution will slowly turn to a nice forest green with time. Overall, the reaction will take about 2 to 3 hours. I advise stirring for longer rather than shorter to make sure that the metallation proceeds to completion. It's not advisable to have any of the intermediate bisanilide chloride 8 complex present upon workup, because it can often result in difficulties in separating the two species at the end of the day. So this mixture here is going to stir for about 3 hours, and when we come back it should be a nice dark forest green. Alright, so the reaction has been stirring for just over 3 hours now. It's this dark green color, and there's a noticeable white precipitate. That's the lithium chloride byproduct. The next step in the procedure is to dry the reaction mixture under reduced pressure. And so what I'm going to do is I'm going to place this little homemade apparatus over the neck of the round bottom flask, and then full vacuum and transfer the volatile components of the reaction mixture to the trap outside the box. And this is just a red rubber septum with a hole punched in it, and a little tube holding the hole open to allow flow of gases. And then it's just a 1420 flow control gas adapter. So just be careful not to open the valve too quickly. Diethyl ether is great, being so volatile it just starts bubbling off. The reaction mixture will likely be dry in about 30 minutes to an hour, depending on your vacuum pump and whether you're pumping off any other volatile components in the box. It's important not to expose the reaction mixture at this point to any halogenated solvents, because the titanium trisanilide will rapidly abstract halogen atoms from any compound it comes in contact with. Well, most any compound, any organic halogen, especially. We start with titanium 3.
Which one? Just quickly.
So yeah, we started with the titanium trichloride.
Oh, okay.
We started with the titanium 3.
Just salt.
And we just did salt metathesis to get the titanium trisanilide. And now we'll let that dry. Alright, so in about an hour, the reaction mixture is dried to give this dark green residue. What we're going to do now is I'm going to add somewhere between 30 and 50 milliliters of Hexane to the reaction vessel. And in the process, I'm going to stir the residue up, try to dissolve as much of the titanium trisanilide as possible, while at the same time precipitating out the lithium chloride byproduct. I'm just freeing the stir bar from the residue in the bottom of the flask. It's kind of sticky in there, and we want to have good stirring to break up the solids. What we're doing here is we're going to try to use the hexane to remove any remaining volatile compounds like THF or TMEDA that are in the residue by breaking everything up and then drying the mixture again. And this will help us separate the lithium chloride from the titanium trisanilide in a filtration step later. But right now the key is to try to break up and dissolve the solids as much as possible with N-hexane. Titanium trisanilide is very soluble in hexane, pentane, so this process works very well. It gives this nice dark green solution with lots of precipitated salt. So again, just Get a nice stirring action going. And then we'll dry it. Try it once more. Just like before. Less than hexane than there was diethyl ether, but given that hexane is less volatile, it'll again take about a half hour, 45 minutes to take the mixture to complete dryness. And get a nice bubbling going on, and that should be good. So the reaction mixture is dried again. It's considerably less tacky than it was before. It's now getting closer to a powder. The light colored solids are the lithium chloride, and then there's a lot of the dark green titanium trisanilide present as well. I'm gonna repeat the drying process one more time with N-hexane, just to ensure that any THF and TMEDA has been completely removed from the reaction mixture, or at least, well, as removed as possible. Can't guarantee that all of the THF and TMEDA will have been evaporated. Again, about 30 to 50 milliliters of hexane to dissolve the titanium trisanilide and precipitate out the lithium chloride. I recommend working as quickly as possible with the material. Again, it's a very sensitive compound, and trace amounts of oxygen, water, halogenated hydrocarbons, all will result in the decomposition. So yeah, just make sure it's stirring well, and then put it back under vacuum. And again, this will take about 30 to 45 minutes. And once it's dry, we'll extract with N-pentane, filter through a bed of sealite to remove lithium chloride, and then the filtrate solution will be placed in the freezer to affect the crystallization of the desired product. Alright, so now the reaction mixture is dry again. At this point, I'm going to extract the titanium trisanilide out of the solids using N-pentane, and I'm going to do the extraction in a series of small extractions to try to minimize the amount of solvent used, because what I want to do is extract, filter, and then save the filtrate and use it directly directly into crystallization to isolate the product. If I use too much N-pentane, attempts to crystallize the titanium trisanilide will be problematic because this filtrate solution will be too dilute. So at this point, I'm adding N-pentane, and I'm just going to add small portions and sort of gauge it by eye. Try to find a minimum amount that needs to be added to dissolve the titanium trisanilide. Then, when I'm done extracting from the flask, I'm going to filter the mixture through this bed of sealite on a coarse fritted funnel, or a fritted funnel with a coarse porosity. and hexane could be used for this step, but the titanium trisanilide really has a nice solubility, temperature-dependent solubility in pentane. So right now, room temperature, roughly 23 degrees Celsius. It's very soluble in pentane. When the filtrate solution is stored at -35, a majority of the titanium trisanilide will crystallize out, whereas it's a little bit more soluble than the N-hexane, and so less crystallizes out upon cooling. Alright, so that's roughly 10 to 20 mils for the first extraction. Really nice dark green solution. Comes through. Good to use the coarse frit with sealite because the lithium chloride salt byproducts are so finely divided that they would normally clog a medium frit without sealite. Sealite's just a very nice filtering aid. The salts that are collected on the frit should be just off-white once all the titanium trisanilide has been extracted. That's most of the material's been transferred. Now, there's going to be a lot of titanium trisanilide sort of caked into the salt byproducts. And really the best way to get that out is to remove the vacuum, break the vacuum in the flask so it doesn't pull the solution through anymore. Add in pentane, washing the sides of the frit. Gently swirl the frit to break up the salts. That'll expose any titanium trisanilide to solvent and help dissolve anything trapped. It's also helpful to sort of maximize the dissolution of the titanium trisanilide to physically stir the filter cake. This is helpful for a lot of filtrations. Dr. James Mayer at Washington stressed this in our inorganic synthesis lab. If you just simply wash a filter cake with solvent, you run the risk of just having the solvent wash over your product and then actually dissolve it. Stirring helps prevent that or breaking up any solid chunks. Okay, so I think that's about enough pentane. The filter cake is going to be pretty free of any green color. So we've used about 50 mils of pentane to do the extraction. Okay, so now with this extraction complete, I'm going to cap up the flask with some rubber septa and transfer the flask to the freezer. Little 1420 rubber septa work well for the sidearms. Give a nice seal, and then the 2440 septa work well for the necks. Okay, and so that's the final solution. There's already some titanium trisanilide sort of coating the sides of the flask. That's okay for the crystallization. That means that we're really concentrated, so we should be able to get a pretty good crop on the first crystallization. So now that'll go in the freezer, and overnight, well, I guess approximately 6 hours to overnight crystals should form. So the filter flask with the titanium trisanilide and pentane is set in the freezer overnight, and I'm going to isolate the crystalline product. Just crystallizes out on the bottom of the flask in nice large prismatic dark green crystals. So I'm going to collect them using vacuum filtration. Going to collect them on this medium porosity pretty funnel. So you can see nice crystals of the product. Dislodge them from the bottom of the flask. And then gently rinse out the flask with a little bit of N-pentane to get any of the crystals that are a little bit stubborn. Also gives you a chance to wash away potentially any organic pentane soluble impurities that may be adhering to the surface of the crystals. But you get a pretty complete transfer. Pull vacuum to make sure most of the pentane's gone through. And then the crystals can be dried under reduced pressure. Dried under reduced pressure directly on the frit. And then once they dry, can determine the mass of the product collected. The filtrate can be further concentrated and set up for additional crystallization of any of other remaining titanium trisanilide that's in solution. And with that, that's the synthesis of titanium trisanilide started from the titanium trichloride tris THF.